All right, let's take a look at equivalence classes. So basically, this is a strategy for identifying particular values, right, that might be representative of an entire range of values that we need to consider. That if we can guarantee that it works for a particular value, we can be confident that it will also work for an entire family of values. Right? So we need to address the fact that in a multivariate application, all sorts of things could go wrong. That and the combinations between those variables gives a combinatorial explosion of all the things that need to be tested. We need to be able to manage that combinatorial explosion, and equivalence classes is one strategy of doing that. So what equivalence partitioning does is that it looks at the input values, and the values could potentially have infinite different possible values, and it looks at being able to perhaps break it up into logical boundaries, logical areas that any particular value in that range might be representative of the entire range, right? So that we don't have to, we can define something that might be potentially infinite into something that is much more manageable. Okay. So identifying these equivalents, right, of these values are equivalent to a whole set of values is important for reducing the number of tests and still maintain a level of confidence that we are testing. We're maintaining the quality that we're looking for. Okay. Yeah. So typically, if you can exercise the same solution, for the same input, typically you'll get the same defect, right? That if you're able to validate that it works for a subset of the values, then you can be guaranteed that it works for the rest, or vice versa. That if it breaks for a particular set of values, it'll also break for other set of values, right? In that same class, that we're looking for these, representatives, values that can stand in place of other values, right? So let's consider this simple function, save at, that takes as input values at a plus b, and the only thing that it's doing is that it's adding them, right? And now adding them would be fine if the values of a and b are within a particular range, right? But if the values a and b are outside of the range that can be represented by a computer, then we would have a problem, right? If as long as you stay within max int and min int, right, everything's okay, all right. So knowing that we have these ranges of they might be huge ranges, but nevertheless they are finite ranges. We need to look at those edges and identify what those edges are, and make sure that our application handles those edges correctly. Right? So something as simple as this, we need to consider all the different possibilities that A and B could take, right? And in a 32-bit or 64-bit machine, there could be huge numbers of considerations that we might need to consider, but not all of them. We need to consider all the billions of possibilities. First of all, we need to identify that these are the three things that could go wrong, perhaps, right? Could be that it could go overflow in one direction. It could underflow, right? It could go negative in the other direction, or none of them. Everything could be okay, right? If I'm looking for these boundaries, what are the values of A and B that might cause me a problem, right? Now in this case, it's pretty simple, right? We know that as you add them as you add A and B, the resulting value can never be more than whatever the computer whatever the operating system can represent, right? So it's just a line, right? That's a straight line that represents the boundary of what the combination of A and B could be. And if you're inside any combination of A and B, well, either 0 or all the way to max int or min int, that you're okay, you're in a valid zone. So we're interested in identifying that there's an area that is okay and there's an area that is not okay, right? And that all the values inside of the valid zone, any one combination of values of A and B in there is okay, right? That if my algorithm works for any two values in A and B, I can guarantee that it works for all the other values inside of that triangle, right? Without me having to exhaustively consider all the possibilities. Okay. Or, for instance, if a variable might be a month, something as simple as a month, I could try to identify what are the classes that can identify whether I'm handling a month correctly. And here we see that it would be we identify a couple of invalid partitions or areas that we know it's invalid, right? Values of 0 and 13 or above 13 or less than 0. And things that are correctly, right, that go between 1 and 12. Any values between those are okay. Right? So as long as our algorithm is within those, we know it's valid. So anyway, so we can choose any values within the month range as a representative of that valid partition. Right? And any values of 13 and above or 0 and below as representatives of the invalid partitions. Make sense? Right? So that we don't have to consider all the infinite numbers from 0 to minus infinity and all the numbers between 13 and plus infinity. Right? Another example, here's a little longer example, is an application here called boat ventures for folks that want to charter a boat, right? And depending on different rules, whether you have a license, how long you're going to be out there, whether you want a captain on board or you want somebody to crew the ship, or how many folks are coming with you, with all sorts of multivariate inputs. Can we calculate what are the valid behaviors of this application? So let's start with something as simple as, how long do you want to charter this boat for, right? And typically it would be that anything that is bigger than 0 is okay, right? You can take it for a day or two or a week or a month, or just take it. It's yours. But obviously the other end of the spectrum is. Certainly 0 makes no sense, right? That you're going to keep it for 0 days, or anything negative makes no sense. So right here we immediately identify two partitions, right? What are going to be referred to as the valid partition and the invalid partition, right? So at this very rough analysis of the partitions, we identify these particular two partitions. We can consider a little more nuanced on other rules. But at a minimum, we have these two partitions. Everybody okay? All right. Right. So we can choose any number, any particular number in these families of partitions to be representative of the entire class. We can choose maybe 0 to represent all the invalid values, and we could choose maybe 10 as being the representative of all the valid values. So our algorithm, to test our algorithm, whatever our algorithm is, we would only have to choose test for 10 and 0, right? And feel confident that perhaps the algorithm will behave correctly for all numbers from 1 all the way to infinity, or from 0 down to minus infinity. All right, so let's become a little bit more nuanced, right? Add a couple more rules to this application, and so that see how it affects the boundaries that we might want to consider, right? The classes that we might want to consider. For instance, one of the rules might say that if the charter is over 7 days, right, then you get a 10% discount. Okay, so here is where we need to start considering the strategy of using boundary value analysis, right? Because notice that this particular word or sentence that says over 7 days might have different interpretations. Do you mean including 7 days, or do you mean strictly over 7 days, meaning 8 days and above? Right. So depending on how you interpret this, you might implement it as this, right? Booking days greater than 0, or it could be greater than or equal to 7, right? And depending on that interpretation, it behaves one way or another. So here's where, combined with classes, right? This is yet another additional technique for being able to identify what tests do you want to consider. right? So for instance, we're not quite sure how to interpret over 7 days. If it's equals to 7, greater than 7, greater than or equal to 7, right? So we certainly need to consider this, right? This boundary, and the typical solution is to focus on that number 7, right? And create test cases that will test your algorithm right before that boundary, at the boundary, and right above that boundary, right? And see if it behaves correctly, if it's doing the right thing. So we would consider numbers, for instance, such as 6, 7, and 8. And we would write tests, 3 test cases, that would test our algorithm at 6, at 7, and at 8. Make sense? Right. So that's the idea of boundary value analysis. We want to be able to consider those edge cases. And these edge cases are all over the place in our algorithms, right? Whenever we have a counter, a loop, an if statement, whenever we're comparing two numbers, those are all potential cases where we might be misinterpreting, and those if statements, is where or those loops are going to allow us to identify those edge cases and create the test cases for our algorithm. All right. So yeah, in general, this is the strategy, right? Whenever you have a boundary, you're going to consider values that are just inside that boundary, just at the very last valid value in that boundary, and then the boundaries that are right outside of that boundary that are invalid. Okay, so valid in just inside the boundary, right at the edge of the boundary, and then right outside of the boundary. Okay. Now, considering this overall strategy, considering that this 3-step strategy, right, of right inside, at the edge, and then right outside, they are, depending on the type of variable that you have, there are different strategies that you might want to consider, right, depending on how your data is distributed, right? What type of data do you have? Right? So, for instance, if you have a value, a variable that has a very specific min-max range, which is contiguous, a contiguous range of values, right? Certainly that's something that you need to consider. Or it might be that you have multiple ranges that are not necessarily contiguous, right? That you have some ranges that are applicable maybe in the summer and the fall, but are not applicable in the spring and the winter, for instance, okay? Or are only valid during holidays in the different seasons, holiday seasons. You might have different ranges all across, spread over the entire year, right? And so you need tests that take into account the multiple ranges. Yes. Another one is that they are not numerical at all, right? That they're not numbers that you can represent as an equation or arithmetically. Instead, they're derived from some subset of enumerated data types, right? That have some valid values, and you need to test whether your application behaves correctly for values that are in that range of that enumerated data types, or are not in that range. Yes, and that perhaps all those ranges, all those enumerated values, they're all treated the same, right? Maybe you treat every day of the week you treat them the same, right? And so any weekday, you might want to try it out. You might want to create a test for the days of the week, and any day of the week would be the same, right? If I test it with Mondays, it should also work for Thursdays, right? And then try with an invalid value, maybe perhaps a weekend day, or you try with Saturday and Sunday, perhaps it should be the invalid value that you test your algorithm with. Make sense, right? So consider a set of valid values that are treated all the same, or valid values that are not necessarily treated all the same, right? That you might have, valid values that are not might have different weightage. Perhaps you might have different seasons, fall, winter, summer, and spring, and you might have a different discount right? For different stages of the year, right? Or you might have different discounts if this is on weekdays or weekends or holidays, and these ranges might be treated in a separate way. Or your input is it's binary, right? It's true or false, and whether it's and then it drives the logic to either apply a behavior or don't apply that behavior. So those are in essence, a range of set of considerations that you might use to derive these tests depending on your particular circumstances. Let's look at each one at a time, and let's look at some examples on what they would look like. For instance, let's look at the one where a value is taken from a specific min-max, so from a specific range. An example of what a requirement might look like is, for instance, a bareboat charter must be between 1 and 21 days, right? So a bareboat charter means that you make yourself fully responsible for the boat, right? You take it out, and as long as we have your credit card on file, you're fully responsible for it in returning it whenever you say you're going to return it, right? Meaning there's no captain on board, no necessary. You're fully responsible. So anyway, so the rule says bareboat charters must be between 1 and 21 days, right? So that's a range, right? So the length of the charter has to be between those two ranges, right? So the valid values will be right inside, right? Any values right inside of the range, at the range, right? At the very last edge of that value, plus the values that are right outside of that range. So you should consider all those values. So for instance, 1 and 21 are valid values, are at the edge, right? And then you have the invalid cases where you have right below or right above those that particular range. So that's an example of creating these classes using it, just graphically representing the same thing. Here's another example where the ranges are not necessarily contiguous, or might not even be related to one another, right? That you have multiple ranges with different rules, right? Where, for instance, you might say, the maximum length of a cruise charter, meaning a captain comes with you and maybe you have a cook on board, right, that cooks for you. So if you have a maximum length of a cruise charter is 14 days. But at the 7th day, from day 7 to 14, right, they're gonna charge you more. Right? So one type of fee applies if it's between 1 and 6 days, but if it's from 7 on, right, we're gonna give you a surcharge. So again, there's two separate rules, right, two separate ranges, right, that need to be considered together. So again, we have some valid values for specific ranges, 1 and 14 for one of the ranges, and 7 and 8 at the edge of 7 days, right? We already have one for the second range, right? And also we consider the invalid data. So this allows us to identify, the sample tests that you would want to validate this particular algorithm of what the surcharge is, right? What the base price is of the charter plus any surcharges depending on the number of days and whether it's crewed or not, right? So there'll be some algorithm that takes into account all these things. How long is it? Is it crewed, right? And how many how many people are on board and blah blah blah. And then taking all these things into account, consider all these valid data and testing all this invalid data, see if the algorithm is correctly calculating the values. So here's the two. Here are the two separate ranges for the crew charter and the surcharge between 7 and 14 days, graphically represented. Now, as more rules are taken into account, this becomes less and less easy to represent. You might have a 2, 3, 4, 5 dimensional space trying to represent all these things. It becomes much harder to consider. Let's take a look at also now in the case where the input is taken from a drop-down or some valid values from a enumerated data type, right? So for instance, it might be that the port of embarkation must be either in Falmouth, Oak Bluffs, or Vineyard Haven. So meaning you can only get on a boat in one of these three cities, one of these three ports, right? So these are all the valid values. and they are all treated the same. It doesn't matter which one, right? So you can choose any of the valid values as a valid test case, right? And then choose anything that is outside of this range as an invalid case. For instance, Woods Hole might be the invalid value, right? Any other range, any other choice that is not in that range, right? Now these are all treated the same. If instead they would be all treated differently, then you would have to test each one individually. Right? So for instance, if the rule says that, if you get on Falmouth, you get a 10% surcharge, right? If you get on Oak Bluffs, you get a 20% surcharge, right? But if you get on Martha's Vineyard, you get a 30% surcharge, right? So these are all valid, but they're all treated differently, right? So you need to test them individually. You need to have separate test cases for each one individually, even though they're all valid, right? And then test case the invalid as well as Woods Hole. And finally, the other option would be if a variable might be a true or false, a binary option, right? Where, for instance, the rule might be that the bareboat charter, whoever is taking out the boat needs to be licensed, right? Needs to have a valid license, right? Pass the exams and whatnot. And so here, the two test cases that we need to be consider is, checking to see if it's valid. Testing the algorithm with a valid license, and then testing it with an invalid valid, and testing it with an invalid license, right? Another strategy that needs to be considered is if the values that you're considering has any particular behavior or any particular distribution or any particular statistical distribution, right? Or if it has a particular pattern, right? Where instead of considering all possible infinite values, you can focus on that particular pattern. Maybe it's the Fibonacci numbers, or maybe it's a power of 2, or maybe they're prime numbers, or whatever, right? That a particular behavior of the number, so that no longer you don't have to focus on all possible values, but you can focus on just the prime numbers, right? And only test the prime number and a non-prime number, perhaps, right? Or if it's a power of 2. Then focus on any number that is of power of 2, and then a number that is not a power of 2. Right? And so that would allow you also to, again, reduce the number of possible test cases that you need to come up with.